some other folks trickling in or going on. So, welcome to our mini method seminar. Today we are very privileged to have Adam King, who will be defending his dissertation next month. So this will be a good opportunity to share his ideas and get feedback. So he'll be presenting Bayesian analysis of episodic substance abuse data. And I think this is an interesting topic because I think it's very relevant to the work that we do, and hopefully we'll have a pretty, engaging and lively discussion. So I'll turn the floor over to you, Adam. Welcome.
Okay, thank you all for coming. So first of all, this is joint work with my dissertation advisor, Rob Weiss. So let me try this out. Okay, so from the offset, I'll say this talk is mostly non-technical. I tried to keep the number of equations fairly low, but insofar as you'll never meet a grad student who doesn't like talking about their dissertation research, if you have technical questions, please feel free to ask. I'll be more than happy to answer them. Okay, so I'm going to start off today talking about exactly what I mean when I say episodic data, and in particular episodic drug abuse data. And then I'll describe the Treatment Utilization and Effectiveness Project, which is one of the many data sets that we have at the integrated substance abuse programs that use or that result in episodic data. And then I'm going to describe briefly three statistical approaches which are not that commonly used in substance abuse research, especially when you have episodic data sets. The first is event history analysis. So you've all probably heard of survival analysis before. I think in biostatistics and HIV research, you probably refer to event time problems as survival problems. In the social sciences, which is sort of, drug abuse research, lies at the intersection between medicine and social sciences. It's usually called event history analysis. So I'll give a very, very brief introduction to that. Next, I'll talk about semi-parametric and additive models. These are models where if you take a standard regression model, there's an assumption, whether it's a Cox regression or a Poisson regression, the relationship between a predictor variable and the response variable is captured by a linear function. Semi-parametric or additive models relax that assumption and allow you to use an arbitrary smooth function to capture that relationship. And then finally, so we're going to have fairly complicated event history models that have elements like recurrent events and competing risks and things like that, and of course the semi-parametric or additive formulations. And that places a pretty big burden on the computing. So classical ways of doing the computing, frequentist methods, sort of break down, especially when you have discrete data with random effects and smoothing and things like that. So I'm going to give a very, very brief overview of how Bayesian inference works in computing, and I'll give you kind of just a big picture of what the problem is with Bayesian computing and how we solve it. And then this is where the technical details would show up, and I'm happy to answer questions about how it's actually done in the context of these complicated event history models. But I'm just going to describe the idea and declare that what I've done is analogous in higher dimensions to what I'll show you some pictures of in lower dimensions. Okay, and then finally I'm going to give a practical example taken from TUE, the Treatment Utilization and Effectiveness Project. And I'll describe some software I've developed that implements the modeling and also the computing algorithms in a package that should allow us to use general episodic data sets. And then I'll use that software to actually obtain inferences from TUE. Okay, any questions before we get going? No? Okay. Okay, so what do we mean by an episode? Well, an episode is just a time spender in which a certain trait, behavior, or circumstance was continually present for a study subject. And episodic data is very common in many different fields. If you're interested in any general context of a chronic disease, subjects experience episodes of disease activity, episodes of remission, and episodes of treatment. But this is not just confined to medical applications. You could be looking at a study of labor markets in which subjects may experience episodes of schooling, employment, and unemployment. Today, we'll be focusing on drug abuse applications, and in this case, subjects experience episodes of drug use, abstinence from drug use, drug treatment, and also incarceration is very prominent. So what's happened in substance abuse research is that instead of analyzing the episodic data directly, what often happens is instead what's analyzed is what I'm calling aggregate summaries of episodes. So what will happen is you'll record episodes or time segments on which someone is using drugs and then not using drugs, but what actually happens is time is sort of discretized into chunks of, say, 6 months, and then some summary of drug use over that time period, such as the total number of days or a percentage of the time the person is using the drug, will actually be computed. So I'm calling that an aggregate summary, and then that's treated as sort of a longitudinal outcome variable. So I would argue that viewing episodic data as episodic data instead of viewing summaries of episodic data is better, and the reason for that is that suppose you observe an association between two different things. So if you're looking at incarceration and drug use, you could look over a 6-month span and say, okay, half the time they were using drugs and a quarter of the time they were incarcerated. What can you infer from that? But if you are looking at episodic data directly, you might see that, say, they were not using drugs for a quarter of the time, then using drugs for a quarter of the time, then were incarcerated for the rest of the time. And that paying attention to these temporal relationships will maybe better help us assess which directions the causal effects go in. Because, I mean, for questions like incarceration and drug use, it could very well be plausible that drug use is causing incarceration, or incarceration is leading to additional drug use. In fact, probably both of those things are happening, and it's of interest to estimate the magnitudes of those relationships.
It's just, this door's weird. We have a lot of spirits that all the time.
Okay, so the Treatment Utilization and Effectiveness Project was a study of illicit drug users. It was conducted in Los Angeles County in the mid-1990s. It was funded by NIDA and was conducted actually here at UCLA at the Integrated Substance Abuse Program's predecessor organization. So initially, 5,000 subjects were contacted and completed baseline interviews. And one difference of TUE versus a lot of other substance abuse research projects is that in many cases in prior substance abuse research, subjects were recruited from drug treatment facilities. But of course, if you're just recruiting from drug treatment facilities, you're only getting people who have been exposed to research. So in a sense, it might be a biased sample of drug users. So in this case, they wanted to find sources of subjects who maybe didn't previously have access to drug treatment, but they also wanted to find facilities that had a high prevalence of drug use to make sampling practical. So they sampled subjects from jails, STD clinics, and ERs. And the baseline interviews in the urinalysis confirmed that it was successful in that regard because there was a high prevalence of drug use. I'll be talking about cocaine episodes a little bit later. And as you can see, half the jail subjects, about 10% of the STD clinic subjects, and 20% of the ER subjects had positive cocaine urinalysis. And of these 5,000 subjects, we'll be looking at a subsample who completed what was called the natural history interview component. And I have some selection criteria for these subjects, which I think is going to show up a little bit later because it'll explain sort of an odd feature of one of the plots. These NHI subjects had to report use of an illegal drug during the previous year, and selection priority was given to subjects who reported dependent drug use or with an elevated risk of dependent drug use because they were engaging in criminal activity, or with an elevated risk of HIV infection because they were currently intravenous drug users. And eventually we end up with about 500 subjects available for analysis. Okay, so what was this natural history interview? Well, the goal of this was to provide a comprehensive picture of lifetime drug use, drug treatment, and criminal history of the interviewees. And to do this, they actually recorded all lifetime episodes of 13 different types of behaviors and circumstances related to drug use. These episodes are recorded as contiguous segments of whole calendar months, so time here is going to be discrete. The way in which they recorded this is with an interview process known as timeline followback. So with this interview process, the way they do this is, again, we're looking at all lifetime episodes, so you may be looking 20 or even 30 years in the past. So one way they do this is to aid recall. They first set up a timeline of major life events, many of these things from official records. They have arrest records, records of marriages, deaths, and also just broader events in the general population, such as prominent elections and things like that, to sort of anchor the subject's memory. And then with this timeline as sort of a scaffolding, then they go through the 13 different types of behaviors and circumstances and fill in time segments or episodes in which they were using the drug, for example. So this timeline follow-back interview protocol has been shown to have high test-retest reliability over shorter spans. So there have been studies looking at timeline follow-back assessment of daily alcohol use. They've administered the timeline follow-back, waited a couple months, given the same timeline follow-back that covers the same time span, and they've found that it's fairly consistent. And also, I think the screen's shaking a bit. And then in addition, so that shows that it's at least somewhat reliable, and then comparison to other ways of collecting the data have suggested that it performs similarly to other retrospective means of collecting data. So at least it's consistent with other ways of getting the data, but of course it could still be subject to recall bias and things like that. Okay, so this is how much data we have. Here we have the 13 different types of behaviors and circumstances. And you can see, for example, among the 500 or so subjects, about 300 of them reported at least one episode of incarceration. And in total, those 300 subjects contributed about 1,500 episodes of incarceration. So among subjects who were ever incarcerated, they were incarcerated about 5 times. And we actually had one subject who was incarcerated a total of 28 times over the course of their life. We'll also be looking at crack cocaine today. So we had 2,000 episodes of cocaine use from about 400 subjects. And again, we ended up with about 5 episodes of cocaine use per subject, although one subject actually had 19 episodes of cocaine use.
So for each of these behavior types, you have the mean number of episodes. So for each episode, do you have any information on per episode, like the duration, for example?
Yeah, so that's what we're going to be doing. Essentially, ultimately, we're going to be looking at survival models for the lengths of episodes of various kinds. And I can tell you for the example a little bit later, for crack cocaine episodes, they lasted on average 20 months.
Okay. So this person here, or this max 19, that would be 19 periods that the participants said they were an active user, which were then separated by periods of non-use. Separated by periods of
non-use, and those periods of non-use may be because the subject was incarcerated. So what is often happening, especially if they have that many episodes, is you'll see, I'll show you a plot in a little bit. In fact, it might just be the next. Here we go. Okay, so this is, and this will, I think this will answer your question. So in this plot here we have along the x-axis here, we have absolute calendar time. The y-axis is the 13 different types of behaviors and circumstances. A solid colored line segment denotes an episode of the corresponding trait. And so what you can see here is, and also in blue, we have various forms of contact with authority. We have incarceration, parole, various kinds of treatments. In red, we have different kinds of substance use. And then we have things dealing with money at the bottom, employment, crime, and drug dealing. And so what you can see here is that it's pretty common for someone to be using cocaine and then pass into treatment, then wait a short time, resume cocaine use. Also, in addition, though this subject doesn't show it as much, it's very common for someone to use cocaine, bounce into prison, bounce out, and then immediately resume cocaine use. I have one more subject here also. Let's see. And this might show it a little bit more clearly, where you can see there's an episode of cocaine use, and then this perfectly coincides this gap with incarceration. So the person that has 19 episodes is most likely not just quitting and resuming. This person is most likely bouncing in and out of incarceration. And I'll show you some estimates from the model a little bit later that looks at number of previous episodes of cocaine use as a predictor, and you'll see that for people who have had lots of episodes, it's most likely incarceration that's breaking them up. Okay, any questions? Okay, so again, I'm going to focus on 3 statistical approaches. The first is event history analysis, and this is relevant because essentially the approach that we're going to be taking is we're going to be looking at the timings of events where the events of interest are transitions either into or out of episodes. And then we're going to be looking at semi-parametric or additive models, which again relax the assumption covariates have linear effects on the response variables. And then finally, what's going to tie all this together, we'll have a complicated event history model with features such as semi-parametric or additive incorporation of covariates. And what ties this together is going to be the Bayesian way of doing the computation.
Can I ask a question on the previous
Sure.
one? I'm just trying to get my intuition.
Do you want to go back?
I just want to go.
This one?
No, the one before. Before.
This one? There we go.
So I'm curious what the sample skewness is for things where just
You mean for episodes per subject?
yeah, when you have the means there.
Yeah, so I guess, yeah, there aren't histograms or bar plots here, but I mean, going back to, Biostat 100A kinds of analyses, you can kind of see with mean is, I think, always bigger than median here, and so it's definitely very right skewed. You have most people with moderate numbers of episodes, but then you have this long tail where you have these really far outlying people here. So yeah, so there are definitely a small minority of people who are contributing very large amounts of very large numbers of episodes. Okay. Any more questions? Okay, so again, the first thing we're going to talk about is event history analysis. And an event is an occurrence or qualitative change which happens at some specific point in time. And this is sort of just a review of the event history analysis approach as opposed to this approach I discussed earlier where we essentially take time, divide it up into chunks, and analyze some aggregate measure as a standard vanilla longitudinal outcome. And the nice thing about event history analysis approach is that it allows us to answer both whether events occur and if so when they occur, and it does it in one single model. And so we can answer, once we have an event history model, we can answer all of these questions with one model. How likely is it a subject resumes cocaine use following treatment? How likely is it the subject resumes, say, in a set period of time, 12 months? How long do former users remain abstinent on average? If you're a survival analysis expert, you might complain that the mean is not going to be knowable unless we followed up people forever. So you can interpret that as median if you like. And again, this is called survival analysis in biostatistics. Social scientists have the best name for it. They call it event history analysis. That's the most general name. Demographers look at this, they call it mortality analysis. And then in engineering, since they're looking at time until failure of some mechanical component, it's called failure time analysis or reliability theory. Okay, so as far as our specific context of episodic data, what are the events we're interested in? Well, the events of interest are events which begin or end episodes. So if you think back to those plots with those line segments, every dot at the beginning or ending of one of those segments would constitute an event. So our ultimate goal would be to have a simultaneous model of everything in those plots, all of those dots. That's a very ambitious goal and not one that we're going to get to today. But what I'm going to talk about here is what will essentially constitute sort of the building block for what such a model could eventually look like. And that is a model where we have, first of all, competing risks, which are distinct ways or reasons that an episode may begin or end. So with an episode of cocaine use, that episode may end because the subject voluntarily stopped cocaine use, or it could end because the subject was arrested. Those are very importantly different outcomes, and we need a model that should treat them separately. We may also have recurrent events, which are events that subjects experience multiple times. If subjects are followed for many years, they're going to experience this event of ceasing cocaine use most likely multiple times. And then finally, we may have multiple types of events. Since the beginning and ending of episodes are obviously very different events, and once we're simultaneously modeling both entrance to and exit from all possible states, this is called a multi-state model. So we may have a model that simultaneously looks at the risk of beginning cocaine use, leaving cocaine use for incarceration, from an incarcerated state going into cocaine use or going into non-use, etc. Okay, so the most common way that we analyze event time data is with the Cox proportional hazards regression model. This is essentially a regression model for what's called the hazard rate, which is just the probability that the event of interest occurs at some time t, given that the event has not already occurred. And when time t is continuous, we actually have to define this in terms of a limit. Time is actually going to be discrete for the model I'm describing, so it actually is a true probability. And this is also called the instantaneous risk, since it's just the chances that the event of interest occurs in the next instant, given that it has not already occurred. And the most common way to analyze survival time data is with the Cox proportional hazards model. And what this does is it says the hazard rate is equal to a function of our predictors and also, oh, wow. So let's see. Where did that, is that just one slide back? Oh, great. So I guess if you press and hold, it goes one slide back.
Oh, cool. That's cool.
Yeah.
We're
So-
learning new things.
Yeah. So I've written this slightly different from the way you might commonly see the Cox proportional hazards model. Usually it says hazard is equal to a lambda 0 of t, which is called the baseline hazard, times the exponential of our function of our predictor variables. What I've done is I've taken the lambda 0 of t and brought it inside this, this term called the linear predictor to emphasize one feature, which is the Cox proportional hazards model says that the hazard is a function of time and all of our predictor variables, but it says it's an arbitrary unspecified function of time, but it's a linear function of all the other predictor variables. So there's sort of an asymmetry there. Okay, so since there is this asymmetry, since time t gets this special status where it's included with an arbitrary, infinitely flexible function, but all our other covariates are included linearly, we should really ask, what is time t and why is it given this special status? Well, usually time t is time at risk. It's also called gap time or simply duration. And this is the time elapsed from the moment the subject first becomes at risk of event occurrence until the current time point in question. So if the event of interest is ceasing cocaine use, then t denotes how long the current episode of cocaine use has lasted up to that point. But the thing is, other notions of time may have just as important relationships with the hazard rate. So a subject's current age is another notion of time, which is going to be related to the hazard or risk of, say, ceasing cocaine use or beginning cocaine use or becoming incarcerated. Also, current absolute calendar time period is going to be important. As I'll show you a little bit later, we're looking at cocaine users in Los Angeles. We know that in the 1980s there was an explosion of crack cocaine use, so the risk of beginning cocaine use is going to be much higher in, say, 1990 than 1980. So current calendar time is going to be important. Birth cohort, that is year of birth, will be important. Time since last treatment, time since first use of the drug, age at first use of the drug. These are all notions of time which may be just as important as this time t that we commonly use in a Cox proportional hazards model. So why does t get special status in our model? Does it deserve special status? Well, maybe it doesn't deserve special status, but the thing is, the standard method of fitting the Cox proportional hazards model only allows us to include one single arbitrary function of time, one single baseline hazard. So we shouldn't let that limitation of the classical method of inference drive our modeling decisions. And that leads to the notion of semi-parametric or additive models, where we essentially remove that restriction that we have to have these linear relationships. So an additive model in particular replaces the linear predictor, which is this linear function of our predictor variables, with an additive predictor. And essentially what we've done is before the covariate x1, the relationship of x1 with a response is it was linear with slope beta 1. If instead of just a coefficient beta 1, we say beta 1 is actually an arbitrary function, then x1 can have any kind of arbitrary relationship with the response variable. So that's called an additive or a semi-parametric model. Okay, so in summary, what we require now is an estimation procedure that can fit an additive model, and we want an additive model because we want arbitrary functions at least for all our different time scales that we're going to be interested in including. So we want something that can fit an additive model with survival time response variables with some of the features that I've just mentioned, where we want to have time varying covariates, we want to have competing risks, and we want to have recurrent events, among other things. So by the time you add in all these features, it becomes difficult to do the computing from a classical or frequentist standpoint. Okay, are there any questions so far?
Yeah.
Yes.
I do. I very much like the discussion about different angles on time and why that would be important. And it made me reflect on a project where it was either chemotherapy or radiation patients for breast cancer quality of life. And it was complicated because the treatment time frame is different for so the question was how to align time, and we actually really spent a lot of time thinking about it and decided that, the clinical decision that a person might sometimes face is a decision about, I'm kind of on the fence here, should I do chemotherapy or not? And so that we should align the time, at the time of the surgery, and then, so that then T+1 year for the chemotherapy patients includes a lot of time on chemotherapy, but that sort of makes it a fair comparison. Then where do they end up a year from now? And it turned out that if you look at it as an area under the curve calculation, there's a lot of burden for the one group. But if you look at it where they end up a year from now, so it might also depend on a person's loss function too. Back to your thing, I love the discussion, and then when you turned it into since it's hard to do, what we're going to do is kind of not assume that anything's linear and we can't. So, but I loved the discussion, but then I was wondering why not, sort of force the hard work to sort of think about where the comparisons, what comparisons you care about, as opposed to just kind of saying, okay, no, we're going to fit all these covariates and stuff. I'm just curious about sort of a strategic question. Why did you sort of let go of what I thought was sort of an interesting challenge and sort of say, okay, well, now we're going to do something that's really quite general to try to accommodate all the scenarios?
I guess I'd say I think that's a really great thing to discuss, and I've thought about this a lot, and there's been some work along these lines. One thing that some people have done is they've actually, when they have a context where they have multiple time scales, there's a way in which you can, and I think this actually might be testable, whether you can actually boil it, you can derive a pseudo time scale which represents whether, this is hard to say, it was sort of a really neat idea. I think it was by David Clayton or something, where he has a test that says if you have all these time scales, can you derive this pseudo time scale that will incorporate all the information in all these different time scales? And I think that's one approach, which is maybe an automated way of pursuing the avenue that you're suggesting, which is finding out if it can be reduced to sort of an essential nugget. I think in this context, right now, I guess I can kind of see for these different time scales that, I mean, in general, a time scale, it's not time itself that's affecting things. Time is always sort of a surrogate for something else that's going on. And I can imagine in these contexts, each of these time scales representing a very different underlying feature. And I think in that sense that makes me hesitant to try to collapse the timescales into a single timescale or make some sort of decision. And I'll show you a little bit later in these plots that we get significant and interesting and weird shapes and relationships when we fit these models with say 3 timescales included simultaneously. And I guess in a sense I've been afraid to go down your road because I've been afraid to make a mistake. But I think that's a very interesting question, because it may be the case that there's one thing that's dominating the other in importance.
Well, or it might be that different people would call it differently, and so by separate, I mean, I am interested nonetheless in what you did, and I actually wasn't familiar with the Clayton thing, which sounds kind of, but I think that I think so that sort of represents the reverse of what I was suggesting, sort of trying to, since you don't know what your audience might prefer, why don't you try to accommodate all of them at the same time? Which actually I kind of think of as a frequentist perspective. You know, like you don't know what the prior is, so
Sure.
there's something that works prior free.
Sure. So
So it's sort of, I mean, I don't mind mixing Bayesian and frequentist perspectives, but I think it's kind of interesting.
yeah, this may upset this portion of the table right here. I am using Bayesian here for very pragmatic reasons. You're right that essentially what I'm doing is I'm saying I don't want to make any decisions in advance. I just want to let the data inform what's going on. So in that sense, I am being very frequentist, and I'm just sort of incidentally using Bayes in order to get MC so I can fit a complicated model. I hope that's okay.
It's good that
It's now on record,
before your oral exam.
Rob will give you constructive criticism after.
So to calm potential waters, I was just reading an old paper of Don Barry's, who's well known for his Bayesian design, and I just want to not tell you everything about the paper or Don Barry, but to point out that this is the guy that taught a bunch of us to use a sign test for, did something increase from prior to post-treatment. But Don's well known as a rabid Bayesian, so I'll leave it at that. Let you back,
Okay.
back to our regularly scheduled.
So, Adam, I have
Yes.
a couple of questions that, I'm really I appreciate your presentation so far, and I like the way you can kind of visually, look at the episodes, and, like if you kind of do like straightforward analysis, you might say that, yeah, incarceration is a protective effect because, you can't use drugs. So it's like inversely correlated with cocaine use, for example. So I like the visual representation of like the duration of episodes.
Mhm.
So a couple of questions about the episodes. Was there a possibility to, per episode and per, for example, type of episode, were you able to capture like the severity of the episode?
Yeah, so actually with this timeline follow-back thing, they don't just record the raw episodes. For each episode of each type, there's a form which can have up to like 100 questions depending on the episode type, where they just are surveyed a bunch of questions about the episode type. I mean, you have to ask, especially if you're looking back 20-something years in the future. I mean, they'll ask people, what was the total street value of cocaine you used in March of 1979? And so I guess there's questions of reliability, but I think the most important is they often ask how many days per month on average did you use cocaine during that time segment you were using, and so that would be a way to gauge severity. So it's not. I'm taking an approach for now, for simplicity's sake, of just trying to model what was contained in that picture. But for each of those line segments, we have potentially 100 questions also that were answered.
Because I think the type of drugs, so there's like recurrent events, right? So there's, you can capture like polydrug use, but for example, people who are high on cocaine, but might be also drunk on alcohol. So like if you're totally intoxicated, you may not be high functioning, but there might be high functioning individuals who are drunk but still be able to like go day to day without any problems. So I think those drugs, type of drugs, and then the polydrug issue and the severity might have an impact on, whatever outcome that you're assessing, whether it's like, risk behaviors and whatever.
Yeah, I mean, that's a very good point. I think there's a lot more in this data set, and I think there are, I mean, even just not even paying attention to those questions, paying attention to the issue of, as you said, polydrug use, eventually when we get to what I would call a multi-process model, where we're looking at not just people switching in and out of cocaine use, but simultaneously them switching out of other drugs, then the chances of making a transition would depend on not just the fact that they're using cocaine, but if they're using other drugs, maybe that will affect the chances that they might leave cocaine for incarceration if they're using like 5 different drugs. So I mean, there's a lot more information to model here, and I feel like that picture that I showed you, if you attach all those covariates onto each of those segments, then you could keep a statistician busy for a lifetime. Okay, so I want to very quickly go through Bayesian inference because I'm going to try to sell you on why it actually helps you do the computing. So with Bayesian inference in a nutshell, you have three components. The first is a prior probability distribution. This captures the information we have about the parameters of our model prior to having looked at the data. If we believe, for example, we have a regression coefficient, beta 5, and we think it's between 1 and 3 based on the information we have prior to conducting the study, then we might say, a priori, beta 5 has a normal distribution. Oh, I did it again. Let's see, I think that time, let me try this experiment. There we go. So we might say that beta 5 has a normal distribution centered in between 1 and 3 and with a standard deviation chosen so that with 95% chance a priori beta 5 is between 1 and 3. So then once we have a prior distribution, and so I should also mention this is relevant. This is actually how we get the smooth arbitrary functions for the additive semi-parametric part, is we essentially place a prior distribution on what a function looks like that ensures that it ends up being smooth. And so once we have our prior distribution, we also need just a standard statistical model that you're used to building in frequentist statistics. And just to take a very simple example, if we're doing simple linear regression of height on weight, then the likelihood or model just says that the distribution of y given our parameters is going to be normal, centered at the regular regression equation with some variance of the errors. And then finally, once you have a prior probability distribution and your statistical model, the posterior distribution, which captures the knowledge that you have about the parameters after having seen the data, is completely determined by a theorem called Bayes' theorem, which I've written right here. Okay, so Bayes' theorem gives us a way of calculating the posterior distribution, but there are a few problems that stand in the way of actually getting practical, useful information out of this posterior distribution. The first is that this integral in the denominator might be hard to calculate. Beta is in general a vector of parameters, so it's multiple parameters. If you remember from calculus, doing a double integral was annoying and a triple integral was really annoying. If you have, say, random effects in your model and you're doing Bayesian statistics, then beta might be a vector of length 1,000 or something like that. So you don't want to have to do a 1,000 dimensional integral even on a computer. But even if you could get a closed form expression for this, you still may need to do additional work in order to make inferences about practical quantities of interest. So suppose, for example, we're including age in our model and we're representing age with one of those arbitrary functions, which I've written as beta sub age here. If you want to know the risk ratio of event occurrence, suppose I want to compare the risk of incarceration in 30-year-olds to the risk of incarceration in 20-year-olds, that's approximately equal to the exponential of the function evaluated at 30 minus the function evaluated at 20. Even if I have a closed form expression for the posterior distribution, I can't necessarily automatically make an inference about that without doing even more calculations. So there's a solution to this problem, which is to take this posterior distribution, which is a probability distribution, and draw a sample from it. Now, if you can get a large enough sample from your posterior distribution, you can answer almost any question you would ever want to ask about it. For example, if I have a sample right here, and I want to make inferences about this quantity, which again has this practical interpretation of being a risk ratio, then what I do is I just take my sample, I evaluate this expression for each element of this sample, I add them all up and divide by the number of samples, and that gives me a posterior estimate. And so once I have a sample from the posterior distribution, I can make inferences about things doing calculations that you could almost do by hand. So this sort of means that if we want to make inferences in very complicated statistical models, if we're doing it in a Bayesian way, what we really need is to get a sample from the posterior distribution. Okay, so the most common way to do that is with something called a Markov chain. So if I have a sequence of elements that I'm hoping are going to form a sample from the posterior distribution, this sequence or chain is going to have a Markov property if each element of the chain only depends on what the previous one was. And so these elements of the chain all are going to come from the posterior distribution, but what we really want, if you remember back to elementary statistics, is we usually want something called a simple random sample. When we have a Markov chain, it's not a simple random sample because the elements in the chain are actually correlated with one another. And the more correlation there is in this chain, the less information they provide about this probability distribution because they're just moving around this distribution very slowly and not exploring it very well. And we say this means that the chain is mixing slowly within that distribution. And we can reduce the correlation in the chain and speed things up by tuning our algorithms to look at the shape of the posterior distribution. Okay, so this is where some of the sort of statistical research contribution comes in. Again, I'm not going to write out all the equations that make things work for the event history models that I've been working with. What I'm going to do instead is just show you a picture of how things actually work in 2 dimensions, and then you can imagine that for a more complicated statistical model, it's something analogous is what's enabling us to fit these models that I've described. So imagine you have a posterior distribution which has just 2 parameters, beta 1 and beta 2, and you want to obtain inferences from this posterior distribution. You can start one of these Markov chains using the simplest algorithm called the Gibbs sampler. And with the Gibbs sampler, it only allows you to modify 1 parameter at once. So if you're changing beta 1, you can only move left and right. If you're changing beta 2, you can only move up and down. If I want to explore this posterior distribution, which I've written with a sample of 1,000 points right here, if I want to explore this using this Gibbs sampler, the only way I can get from one side to the other is to go over and up, over and up, over and up, over and up. And you can see it takes a very long time to get from one side to the other. Compounding things, that Markov property that I mentioned means that once you've gotten, say, halfway across, you're just as likely to double back as you are to keep going forward. So it can take a very, very long time to explore this probability distribution. But if you redesign your algorithm to take advantage of information about the shape of the distribution, as I've shown in this blue chain here, you can see that you can move much more quickly by designing it to move quickly in the long direction. So what I've done is taken the event history models that I've described with some of those features that I described, the competing risks, the recurrent events, the semi-parametric incorporation of multiple timescales, and I've designed MCMC algorithms which do something analogous to replacing the red chain with the blue chain here. And I've included those in, or I am in the process of including those in an R software package. The functions exist and work at this point, but if you've ever written a software package, you know that when you're writing software for yourself, you know how it works and you know how not to break it. But if you want to publish it for people to use, the first thing that's going to happen is someone's going to put a data frame in the wrong format into your functions, and it's going to break, and they're going to be unhappy. So there's a lot of extra work that goes into making something publishable. So that's one thing I'm working on right now. And how this works is you just pass a collection of covariates to the functions, and these covariates can be specified at the subject level, like you might have the subject's race. They can be at the episode level, like how many previous episodes of cocaine use the person's had, or they can be at the person time level. So this allows you to have time-varying covariates. And an example of a person time level thing is suppose you're looking at episodes of cocaine use. A time-varying covariate might be employment status, because people might become employed or unemployed while using cocaine. Also, age is, in a sense, a continuously varying time-varying covariate, because as you're tracking subjects through time as they're using cocaine, their age is continuously changing. And then this software allows 3 different types of covariates. You can have categorical fixed effects, such as race and sex and things like that. You can have continuous covariates, and these are incorporated with these smooth functions in an additive semi-parametric way, like I described before. And then finally, you can have random effects, subject-specific random effects, which again are going to be necessary because you repeatedly observe, say, episodes of cocaine use, and so you need random effects to account for the correlation between those. These random effects are also allowed to be correlated for the different competing risks. So a subject will have a random effect for the competing risk of incarceration and a random effect for the chances of voluntarily stopping use, and those random effects will be correlated within subjects. And then finally, you have to supply the outcome information, the sensory and competing risks information, and the durations of the episodes. Okay, now I'll give an example of how this software works. So we're going to be looking at, the treatment utilization and effectiveness project data. We're going to be looking at the termination event of recurrent episodes of cocaine use, and we're going to have two competing risks: incarceration and voluntary cessation of drug use. We'll be looking at 400 subjects, all who had at least one cocaine use episode. In total, these subjects are contributing 1,500 cocaine use episodes. 100 of these were right-censored by it being the time of interview, and then among the rest, about half of the episodes ended because the subject was incarcerated, and about half ended because the subject voluntarily stopped use. And on average, the episodes last 20 months. And we included 6 predictor variables plus subject-specific random effects. The continuous variables were time at risk, age, and absolute calendar time. And the categorical variables were number of previous episodes of cocaine use, sex, and race.
Yeah, need to know what the average non-use episode length was after first use?
No. No, not off the top of my head. I might have calculated that
Sometime.
one day.
Just wondering.
And so here, just to remind you what the data looks like, here I have 10 years of history from 10 subjects. In blue is episodes of incarceration. In red is episodes of cocaine use. So the model that we're looking at right now is a model for the durations of these red line segments. And so you can see here with subject number 5, here is an episode of cocaine use which does not end in incarceration, whereas for subject 4, here is an episode of cocaine use which does end with incarceration. Okay, so here are inferences for two of the continuous variables, age and absolute calendar time. In these pictures, the x-axis is of course the predictor variable. The y-axis is hazard rate on a log scale. And in all of these pictures that I'm showing you, blue is going to represent the competing risk of becoming incarcerated, and red is going to represent the competing risk of stopping use for all other reasons. And what you can see here is that, first of all, we definitely didn't want to just use simple linear functions to represent these effects. These effects are very, very nonlinear, as you can see. And I don't think it would have even been easy a priori to specify, say, a quadratic relationship or something like that, because these functions don't really look like any simple quadratic or cubic curve either. So what you can see here is that for subjects that are in their early teens, and we didn't have that many subjects in their early teens, but I think this is very significantly higher than just a few years later still. You can see that they have the highest chances of stopping use for reasons other than incarceration. You can also see that for subjects between 20 and 30, these are in a sense the subjects who are doing the worst. They have about the lowest chances of voluntarily stopping use, and yet have high chances of becoming incarcerated while using drugs. And then finally, you'll see that roughly after the early 40s, both of the risks taper off, which suggests that these are sort of stable cocaine users. They're not voluntarily stopping use, but they're also not becoming arrested. Probably the more interesting picture, I think, is depicting the relationship between absolute calendar time and the risk of these two events. What you'll see, first of all, the most notable feature of this plot is that risks for both events very dramatically increase starting around the year 1980. This is very plausible for incarceration risk. If you'll recall, these are drug users in Los Angeles. As you probably know, there's a crack cocaine epidemic in Los Angeles. So the incarceration rate, which again, we definitely believe the incarceration data to be accurate because this was actually determined from official incarceration records. You can see that the risk of becoming incarcerated very dramatically increases starting around 1980, and that reflects the crack cocaine epidemic and also the law enforcement measures that were put in place around that time. The other sort of surprising thing at first, I think, is the fact that the chances of voluntarily stopping use appear to dramatically increase around the same time, and in fact reach a much higher rate than even the incarceration rate. And I would not, I guess I would presume that actually may not be as much a feature of what was actually really happening. I would say that there are two explanations for that. One might be that there's some selection bias going on. If you remember that one of the criteria for being included in the study is that these had to be recent drug users. So they might have had recent instances of stopping cocaine use in the recent past, and that might explain this curve being so high at that point. It could also be a recall bias effect where people are more likely to recall and being able to differentiate short episodes in the recent past than they would be able to recall short episodes, say, 30 years earlier in 1965. One advantage, though, even though, again, as I've indicated, I'm not sure that I believe that this should be a true feature of what was actually happening. I think it could be due to some combination of selection bias or recall bias. One reason we might want to include this is because, in a sense, by including that as a covariate, we may be sort of adjusting out the effects of those biases, which we have reason to believe is important, because if you don't include absolute calendar time, these estimates of the relationship between age and the risks of stopping use and the risks of incarceration actually change dramatically. The shapes of these curves become very, very different when we don't include this. And I think that's because there may be, again, a recall or selection bias increasing this, but there's an association between age in this data set and calendar time period because, for example, you don't observe subjects who are 50 years old in 1960 in this data set, because such people wouldn't even be alive by the time the study was conducted. So including those might give us more accurate estimates of the age effect. Okay, and then we have two more plots. The first is depicting the relationship of time at risk with the hazards, and probably the most notable thing is that you see that the chances of voluntarily stopping use are much, much, much higher in the very first month of cocaine use than they are at any other time point. And then that dramatically drops off after the first month. And then the other feature that's of interest is around 2 years after they've started cocaine use, they're neither becoming incarcerated nor voluntarily ceasing use at high rates. And then finally, if you look at number of previous episodes of cocaine use, you see an opposite pattern. What you'll see is that if you look at the chances of voluntarily stopping use, it's fairly high after just one episode or having no previous episodes of cocaine use, and it drops. Once you have 5 or more episodes of cocaine use, your chances of voluntarily ceasing drug use become quite low. You see the opposite relationship with incarceration, and this is what I was mentioning earlier. If you have these people, like say that person who's contributed 19 episodes of cocaine use, what's happening is by the time they've had a couple episodes of cocaine use, the reason they're stopping cocaine use and resuming is because this hazard of incarceration is high. So once people have been using for a while, they're not stopping voluntarily, they're stopping voluntarily because they become arrested. Okay, and now I want to briefly mention some future directions for this work. The first is that we have this issue of these time scales, and one problem that commonly shows up is what are called age period cohort type problems. So in these cases, you have time scales which have perfect linear dependence with one another, or perfect multicollinearity. And so the classical example of this is where you have time of birth plus current age is equal to current absolute calendar time. And as you know from fitting any kind of regression model, if you have a collection of covariates, where one of them is essentially a linear combination of the others, you often can't fit the regression model. If you're running a SAS proc reg, it'll give you an error message. And then again, this also shows up in episodic data problems where you have age at first use, or also just age at which a certain disease begins, total duration of drug use, or time since the person first came down with the disease, and that's always equal to current age. So even if you don't have a classical age period cohort problem, often in episodic data problems, you encounter a different form of age period cohort problem. And the question is, maybe we can use prior information in a Bayesian context to try to disentangle these effects. Another thing is extending this competing risk recurrent event history model to a case where we have a full multi-state model. Essentially, as I mentioned earlier, this competing risks recurrent event history model is sort of the building block that allows us to construct these more complicated models, such as the multi-state model. So moving from the current point to this multi-state model is primarily a programming problem to allow users to specify multi-state data and then having essentially multiple copies of the competing risks model run at the same time. And once we do that, we can get some more interesting targets of inference, such as, given that a person has this history and this drug use history and this treatment history, what is the chances that they stay abstinent for the following 10-year period? That's something that we might be able to simulate given our fitted model using a multi-state model. And then finally, the ultimate goal would be what I call a multi-process model, where we're essentially modeling everything in one of those pictures, all 13 different types of behaviors and circumstances, all at the same time. And so, we might be modeling different drugs simultaneously, and also treatment, and also employment, and these things can in general overlap. So that would sort of be the ultimate goal, but there are a number of problems which show up when you start thinking about going that far. Okay, that's it for the talk today. I just want to quickly thank again my advisor Rob Weiss for listening to a version of this talk once a week for a couple years. I also want to thank Dr. Ying Sir from the UCLA Integrated Substance Abuse Programs for providing the data set and also providing mentorship and a place to work on my software. And then finally, I want to thank Amgen for providing my fellowship for the past 2 years. And thank you all for coming.